In 2013, Skittles did the unthinkable. They changed their lime flavor to sour apple. Now, this didn't personally affect my life, but this lesson came from the stats medic teachers, and so Mr. Wilcox, who is a fantastic statistics teacher that has created many of these examples we've used in these videos, this was life-altering. Mr. Wilcox takes a small handful of 5 Skittles from a bin of 10,000. Before we continue, I just want you to picture a bin of 10,000 Skittles. Okay, continue. He gets all green. Tragic. If 20% of the Skittles are green, what's the probability of this happening? Getting 5 out of 5 green. Pause the video and start with just number 1. Is this a binomial setting? Okay, this one is actually not binomial. We do have binary, it's either green or not, so there's 2 outcomes, and we do have a set number of trials. He's only taking out 5 Skittles. However, he's not replacing each Skittle each time. So the probability of getting green is changing ever so slightly each time he picks up a Skittle. And it also means that the Skittles are not independent of each other. We select one Skittle, and now the probabilities that the others are green have changed. Because now there's not 10,000 Skittles, there's 9,999 Skittles. So since this is not binomial, if we want to find the probability of getting 5 green Skittles, we have to go back to what we were doing earlier in the unit. This is an AND scenario. So 20% of the Skittles are green, which means that's 2,000 green Skittles out of 10,000. Pause the video and use the multiplication rule to calculate the probability that you get 5 green Skittles in a row. Whew, okay. 2,000 out of 10,000 for the first Skittle, 1,999 out of 9,999 for the second Skittle, and so on. There's a very small chance that he gets 5 green Skittles in a row. Okay, now let's just compare. Let's see what would have happened if we had accidentally said that this was binomial and calculated it using the binomial distribution. Pause the video and do the same calculation, but this time use the binomial formula. Find the probability that he gets 5 out of 5 green Skittles. So using the formula, we are picking 5 and we want to see the probability of getting all 5 green. Now, this is just 1. You could type that into your calculator, but if you use common sense, you can think, oh, if I want all of them to be successes, there's only one way that I can arrange all those successes. Then we have the probability of success raised to the 5th, probability of failure raised to the 0 because there are no failures. And look at that. Almost the exact same probability. So pause the video and think about this for a moment. Why did we get almost the same answer in 2 and 3? So this has to do with the size of the population. We have a bin of 10,000 Skittles, which once again, just picture a bin of 10,000 Skittles for a moment. Imagine scooping out a handful from a bin of 10,000 Skittles. I want to see that. Selecting Skittles without replacement isn't changing the probability of a Skittle being green that much. And you can see that here. The probability of selecting a green Skittle went from 2,000 out of 10,000 to 1,999 out of 9,999. Not that different. So basically, if your population is large enough, it's okay that you don't replace after each trial. We can assume that there is independence. So we call this assumption the 10% condition or the 10% rule. We are allowed to assume independence if lowercase n, so that's our sample, is small compared to the population, which is capital N. How small, you may be asking? Good question. 10 times little n has to be less than or equal to big N. In other words, the population has to be at least 10 times as big. So since we are taking a sample of 5 Skittles here, the population needs to be at least 50 Skittles. We are well over 50 Skittles. We're at 10,000, so we're definitely fine. Any population over 50 Skittles, and we can assume that each trial is independent, and we can assume that the probability stays the same. This is pretty important. I might put a star or a box or something around it so that you remember it. Okay, Mr. Wilcox is now starting to get hungry. He skipped lunch, and so he takes 100 Skittles from the large bin of 10,000 Skittles. X is going to be the number of green Skittles in his handful of 100. X can be considered binomial because we've met the 10% condition. Now, a really common question is, can you assume independence? And if that was the question, you would write out, yes, we can. 10 times n, here would be 10 times 100, which is only 1,000, and there are more than 1,000 Skittles in our population. So that's why the independent condition, or the 10% condition, is met. Okay, so at this point, pause the video and try just 5 and 6. I will show you a graphic for number 7 that'll help you answer that. So just 5 and 6. So because the distribution is binomial, we can use the formulas for mean and standard deviation. We get a mean of 20, standard deviation of 4. At most, 11 green would be x less than or equal to 11. I used binom CDF. We have 100, probability of success is 0.2. We're interested in 11. There's a 1.26% chance that he gets at most 11 green Skittles. This next question asks about the approximate shape of the distribution. So I actually have an applet. Here I've put in sample size is 100, probability of success is 0.2. Here's what the probabilities look like. So most of the time, if you were to repeat this over and over and over, most of the time you would get 20 green Skittles because the probability of green Skittle is 20%, and we're taking 100 Skittles. That makes sense. You would mostly be within 4 Skittles of the mean because that's our standard deviation, but sometimes you would get more than 4 in either direction. Does that shape look familiar? It should look kind of familiar. Yeah, that's very clearly a normal distribution. So this particular binomial distribution also happens to look normal. So let's just do an experiment here. In number 8, redo, that says number 5, but it should be number 6. Redo number 6, but this time use a normal distribution. So use norm CDF instead of binom CDF. Pause the video now and do that. Okay, so I used the mean and standard deviation from number 5 to calculate a z-score. Plugged it in norm CDF. We have low, upper. Since I'm using the z-score as the upper, I'm using 0 and 1 for the mean and the standard deviation. Oh my gosh, it's almost exactly the same as number 6. So weird. So the question is, was this just a coincidence? Did this distribution happen to be both binomial and normal, and other binomial distributions are not normal? Let's check this out. So I have another applet where you can set the number of trials and the probability, and it'll show you how close to normal it actually is. If the trial is 1, I'm not sure why you would be considering it binomial. Let's make this a more reasonable number and say 10. So there's 10 trials, probability of success 0.7. It's pretty normal. Let's increase probability of success. Now it's actually getting less and less normal, so you can see if I get too far this way, now it's skewed left. And I bet the same thing would happen if I move the probability all the way to the left. Now it's too skewed right. So the probability needs to be somewhere around the middle, around 0.5, and then I get something that looks pretty normal. Let's see what happens if I increase the number of trials. Isn't that just hypnotizing? We'll put you right to sleep. When I increase the number of trials, the distribution gets more and more normal. Now let's see what happens if I slide the probability over to the right. Okay, eventually it does get skewed, but it stays normal much longer than before. Like, it's still pretty normal at 0.91. When trials was down at 10, I was already looking left skewed at that point. So it looks like when we have more trials, we can be a little bit more forgiving of where P is. Now this is all summarized in something we're going to call either the normal condition or the large counts condition. We are allowed to assume the distribution is normal if we have at least 10 successes and at least 10 failures. To calculate the number of successes, we take n times p, number in the trial times the probability. If that's greater than 10, and the number of failures is greater than 10, which is n times 1 minus p, we can safely assume that the distribution is approximately normal. Now I did say approximately, which is partially why we got a slightly different answer here than here, but that's okay. So now you can see why this wasn't quite normal when we had only 10 trials and a probability of 0.24. N times p here doesn't get us a number greater than or equal to 10, which is why if we increase the number of trials, this magically becomes more normal. Now we can safely say, yes, we have at least 10 successes and at least 10 failures. So it's kind of a tricky way to ensure that the binomial distribution looks normal. We're going to be using this so much, I would also put a star or a box or something around this condition. Okay, you now have enough information to do the check your understanding on the next page. Pause the video, do as much as you can, and then we'll debrief together. So for this distribution, all 4 conditions are met to make it binomial. We have 2 outcomes. They either have a credit card or they don't. Independent, we can use the 10% condition and say It's reasonable to assume that there are more than 5,000 teenagers in the US who are between the ages of 14 and 18. That's because our sample size is 500. We multiply that by 10. That gives us like the lower limit of what our population has to be. It has to be greater than 5,000. And we have a set number of trials, which is 500, and the probability of success is the same on each trial. Okay, on your version it's fixed. This should say 14%. It's been a day. Sorry. Okay, use the binomial distribution to estimate the probability that 50 or fewer teens have debit cards. Debit cards? How is credit cards? Wow, I've really read a lot of things in this problem wrong. All right, this is x less than or equal to 50, so binom CDF, n is 500, p is 0.14, x is 50, and there's our probability. Very low chance that 50 or fewer teens have debit cards. Okay, justify why x can be approximated by a normal distribution. Well, we check our normal condition. N times p is 70, that's the number of successes. N times 1 minus p, that's the number of fails, 430. Both of those are well above 10, so we can assume that we have an approximately normal distribution. I just want to point out the word approximate here. When you're writing in a free response question, you want to say, therefore we can conclude the distribution is approximately normal. Always say approximately. And finally, to use the normal distribution, you first need to know the mean and the standard deviation, so we do that using the mean and standard deviation formulas, calculate a z-score, plug it into norm CDF, almost the exact same answer. If you have questions on the normal part, remember you can go back to Unit 1 and watch some of the normal probability practice questions. That would be very helpful just to review since it's been a while. As I mentioned in the previous video, sometimes the hardest part of binomial distributions is encountering them in the wild and recognizing that they're binomial, which is why practicing it now will make reviewing much easier later. And as we've seen in this video, the nice thing about binomial distributions is quite often they are also normal distributions, which opens up a whole new set of tools that we can use to answer these questions.